to Modulation Distortion, a better way to test. This is episode 2 of Space Talk, a series of short and hopefully useful webcasts that will give you some insight into the space and satellite industry, as well as the test and measurement challenges faced therein. My name's Richard Soden. I'm the Space and Satellite Application Lead at Keysight and confirmed Space Geek. I've got a background in optoelectronics, laser systems and instrumentation, and I've been working with Keysight for over 15 years, and I work in our Swiss offices. My background in applications was in big physics and power amplifier characterization, digital pre-distortion for telecom, and for the last 5 to 6 years I've been working exclusively on space and satellite applications with some of my other Space Geek colleagues. In this series, I'll be joined by Mark Lombardi and Ian Furness. Mark's got over 25 years of experience in power, time, and frequency domain measurements in devices and flight hardware. He's been working in satellite and modem with satellite and modem developers, with hardware in the loop for communication verification. Ian is relatively new to Keysight and the test and measurement world, but he's a confirmed engineer and owned his own electrical contractor in business. Ian is also a proud space geek with Mark and myself, and is very excited about the space industry. In each episode of this series, we'll be joined by an expert who will be our guest speaker to talk about a specific challenge or measurement requirement in the market. Mark, Ian, and I will be chatting and asking these experts, asking them questions about the challenges and looking at the solutions for the market. Hopefully we'll get this all done in under 30 minutes and we'll all learn something new and have a bit of fun on the way. If you have any questions, please put those into the Q&A chat from the widget below. We'll try and answer those with some of my colleagues. We'll be furiously answering questions in chat. If they can't answer all of those questions, we'll get back to you. They're recorded, and myself or one of the team will follow up on every single one of those questions that comes up. So this week, we're joined by our friend and colleague Donald van der Weyt, with whom we'll be talking about modulation distortion, which I've done presentations on this, and I think it's a fascinating and genius method of making wideband measurements with a network analyzer. So, Donald, could you just say a couple of words about yourself, introduce yourself?
Sure. Hi, everybody. So, yeah, Donald van der Weyt. I'm an application engineer with Keysight Technologies. I've been with Keysight for 14 years now, here in Southern California. So I think I'm probably your first presenter from Los Angeles in this series, I'm guessing. And,
you're our first presenter.
So, Southern California is kind of a hotbed for aerospace. So I guess I've always been involved in aerospace defense technology, satellite technology, and so forth. And always working with things in the electromagnetic spectrum, either radar or electronic warfare, or now space and satellite communications. So great to be here.
Yeah, thanks, Donald. So, Donald, one of the things, so you're our first guest speaker, an expert, and one of the things I'm going to ask all of our guests is, where is the importance in what the subject matter is in this? And we're going to talk about modulation distortion, and that's wideband measurements. And I think what this links to is really the growing requirements for wideband measurements and wideband data transfer, right? There's a huge amount of data going through satellite links, and that means wideband signals. And the question is, how does that all link up? Am I right? Am I wrong? Did we lose Donald?
We lost Donald. Oh, he's back.
Donald's back.
There's a quick example of why we need testing in these networks.
Thank you, Donald.
I got your question, and I understand there's so many tests that can be done on satellite link. So why modulation distortion? Why is that important? And you really hit the nail on the head. As people are trying to more and more data through links and satellites, they're running into problems like distortion coming up in ways that they haven't come up before. I mean, it used to be in a satellite you'd send kind of a single carrier thing, 40 megahertz, 80 megahertz. People are now sending more like gigahertz signals over these satellite links. And as we get these wideband signals going through, it's one thing to do that on the ground, cable or so forth, but in space, we have to broadcast these a long way and with a lot of power. So it goes to a power amplifier. And these power amplifiers are never operated in a linear range. They're always in kind of a compression range. And there's a lot of distortion there. So then the question is, what's that going to do to my signal? And it's a big design problem. People have to design around the inherent distortion that's built into the system. So before you can design around that, you got to measure it. So
right.
That's kind of where we come in on our team. And Richard, you hinted about a new technique that we have there, and that's mostly what I'll be talking about today. We've kind of taken techniques that existed in the industry for a long time, and we've built on them, and we've got some real new insights there. So here's
okay. So you're going to walk us through this, yeah?
Oh yeah, sure. I'll kind of go with an example that most people know about. When you're testing a wideband link, like an amplifier or an up converter, down converter, there's a lot of different metrics you can use to kind of get an idea of the quality of the signal as it goes through that link. And we got one here on a slide, a noise power ratio. I'm fond of this one because it goes back to the 1930s and 40s. It's an old Bell Labs thing where they used to send a lot of analog telephone signals down a trunk line, for example. They would just combine them. They would frequency division multiplex them together, so they'd have this kind of a wide band of narrow signals. And then they'd pass it through amplifiers. The amplifiers would add distortion. And so the obvious question is, what's the effect of the distortion of the amplifier? What's the effect of all the other channels on any given channel? So they did a clever thing. They said, well, we'll leave one channel out. We'll leave the energy out of one channel. You can see on the slide here. We'll make a notch in the signal, and we'll fill up all the other channels, and we'll pass it down through the amplifier, and we'll see how much that fills in. We can kind of get an idea then of how much distortion is being created in any given area. And they measure the ratio of that noise to the power that would have been there, and they call that the noise power ratio. They've been doing that for years, and it's a fairly effective test. But there's a lot of things where it kind of falls short. I mean, you really take into account what the distortion was before it goes in. You can't really manipulate the signal very well. The signal's kind of fixed for what it is. It might not be the signal that you eventually want to test with. So in addition to that noise power ratio, that distortion, and I think, Mark, you were one that pointed this out to me. You say, well, really, another facet of exactly the same thing is the ACPR, the adjacent channel power ratio, where we get spectral regrowth coming up outside the channel. And it's really all a function of the same mechanism in the distortion, where different frequencies of the signal are mixing effectively with other frequencies in the signal and creating frequencies in places you might not expect.
Yeah, and as you point out, this topic is really important because ultimately, it's while you can fix with filters some of the linear distortion, this nonlinear distortion is something you really have to kind of work around, both in the channel and out of the channel, and especially in satellite communications, you have masks that have to be conformed to for regulatory reasons.
Yeah, and you want to be a good neighbor, right? That's the other thing, right? So all that ACPR is all of that energy leaking out of your channel into the adjacent channels, and that could be somebody else's modem or somebody else's communication link. It's a very interesting problem to be solving. So, Donald, are you going to stay with us?
Yeah, well, I keep saying I'm disconnected by another participant, and I hope I haven't offended anyone out there. Let's see.
Not yet, but we're still pretty early into the recording. So,
Yeah.
So it's an excellent point, Mark and Richard. You're saying that linear distortion is one thing to deal with, and actually there's a lot of mechanisms for dealing with that. There are some mechanisms for dealing with nonlinear distortion, but it's a lot harder. And again, before you can do anything about it, you have to see it. You have to be able to measure it. So we came up with this system. I think we've got the next slide on this. We came up with a system using our network analyzer to analyze this distortion, where we coupled the network analyzer with a wideband source. So the network analyzer usually just has a narrowband source in it. You use one tone or two tones, you sweep across. But that doesn't really work for this kind of distortion. You have to put in a wideband signal to be able to see it. So we add a wideband source on the side there with the network analyzer. When you think about tests like NPR, are basically component tests at heart, right? It's I've got this device, tell me how much distortion this device or the system is adding. So it's really a component test. So using a component tester like a network analyzer is a very natural choice. It gives us a chance to see the signal going into the device under test. About the signal that way. So wideband source and use it to generate that wideband signal. Let's see, the next slide there, I think it shows PR signals going in and out of the source. Yeah, there we go. Yeah, so there's a screen capture of this technology, and I'll walk you around here a little bit and show you what's different about the way that we do it. If you look at the blue trace, that's basically an NPR signal right there. So I've got a pedestal, and I've carved a notch in the middle of it where the power would load up. And if you just focus on the blue signal, you see that notch is pretty deep. Inside the notch in the center of the screen there, it's way down at the bottom.
Yeah.
The yellow trace is the trace of the device. Again, it's a very typical NPR test. Now, we've got a pretty good amount of distortion in this amplifier here. And you can see on that yellow trace that the notch is really filled up with a lot of noise. The notch that was probably, 50 dB down and more is now only about 30 dB down. So it's really filled up with distortion there. And you can see on either side of the signal, on the left and the right, that adjacent channel power, where what people refer to as spectral regrowth, where again the distortion of the signal, it's not just messing up your signal, now it's messing up the signal of the link next to you too, which makes you real popular. So you got to have that under control as well. So it used to be people would send this noise power ratio signal through the amplifier, and they would see the yellow trace come out, and they would take out their screen calipers and do a quick measurement there and say, yeah, okay, my noise power ratio, and be done. But we added something to that. We've got a new technology based on a method called spectral correlation. And what spectral correlation does is it isolates that nonlinear distortion. It kind of separates the nonlinear distortion and the linear distortion as it goes through the link. And we can display the nonlinear distortion. So now on the screen you see it, there's a green trace kind of cutting through the middle there. The reason you don't see the green trace go from side to side on the screen is because it's pretty much coincident with the yellow trace as we go across. But that's a trace of just the nonlinear distortion. So we don't have to have that notch to see it anymore. We can just take a look at the distortion as it goes across. So that's kind of, we're able to see distortion in a way that we've never been able to see it before. We can see it, we can see the shape of it. We can see it anywhere inside or outside the channel. It's giving us a lot more insight into what's actually there.
Yeah, this is a really interesting dynamic for me, Donald, because I realized over time one of the things with NPR was there was so much discussion about, well, how wide should the notch be based on the whole waveform, and there was a lot of IP, intellectual property, or even uncertainty about how those things interacted with each other. And I think one of the things we're learning with this technique is really some discipline about, well, we can actually predict what's going on and understand much better now that we have this way of kind of peeling back the waveform and looking at what's underneath. And we're seeing how much impact the CCDF curve has and the spectral components have to the results. So I think, you can correct me if I'm wrong, but we've started to demystify some of what was once a mystery.
Oh, I'm glad you mentioned that, because when I was doing NPR tests, there were two things that drove me nuts. And one was you always had to clean up the signal continuously, so you had that deep notch, so that you knew the notch wasn't interfering with your measurement. And we can get rid of the notch now. We can see the distortion with or without it. But the other one that just drove me crazy is people were only able to measure the distortion as it was actually in the notch. And so, and you can see this is a very Well, it's noise power ratio. It's a noise-like process. So out of that noise, how do you get the number that you want? Do you average it? Do you take the highest one, the lowest one? And if you're only dealing with the signal that's in the notch, you have a very small sample size for that. Here, it's a repeatable measurement of a noise-like signal. You can reduce the uncertainty almost arbitrarily, statistically, with this. So there was always the question, it's like, well, I need a wide enough notch so I can see if the NPR, I can really get enough samples in there. People used to say, oh, I have to have 100 tones in my notch or something like that. It's not even an issue anymore. You've got a much, much broader sample rate there. You can see what's actually going on and reduce the uncertainty.
Richard, I've been sitting over here listening to you and thinking on what you said in the first slide. And you said that this was a test, NPR. I'm not too familiar with it, but it was a test that was developed by Bell Labs in the 30s and 40s, used on analog telephone systems. So is that still is this still a commonly used relevant test for the satellite industry? I mean, it seems kind of outdated and maybe not completely useful.
I have a bias about that. Yeah. The concept is very valid, because really what they're trying to do is measure a ratio of the distortion to the signal, and that's perfectly valid. It's the method. It's the method that I think is a little bit outdated, and I'll talk about that in just a little bit. And one of the reasons that NPR stuck around so long, let's compare it to another distortion measurement. EVM is another distortion measurement. Error vector magnitude. That's kind of a symbol domain thing where we're looking at what's the error in each individual symbol, and that's great. But EVM also includes linear effects. It can include effects. You could have a bad IQ modulator and do quadrature distortion, things like that. One of the reasons NPR sticks around is because it really isolates the nonlinear response of this amplifier and shows the amount of distortion. I guess it's probably closer to a two-tone intermodulation distortion test. But there again, with a two-tone test, you've got very limited data. You've kind of got two tones going in, and you see data points for the distortion on either side. NPR fills up the channel with signal, and I think that's one of the reasons that people like it.
Yeah, and I think the other thing I've noticed... Oh, sorry, Richard. I was just going to say...
Sorry, we're all jumping over each other because I know I like it. No, but what you just said, Donald, I think from the two-tone and moving over to an NPR is a little bit what we're doing now, right, with modulation distortion, because two-tone is a narrow band, well, it's tones, right? It's CW. Right? And you go to an NPR, which gives you a bit more detail on a wider bandwidth signal and how that will be. But then to go from that NPR into modulation, or the spectral correlation method, that gives you even more data, right? It gives you something that's more typical. And I should say, I've been working with this modulation distortion as well in the past, and I'm if I'm smiling, it's because I'm kind of excited about it as well. So.
Yeah, Richard, the only thing I was going to add to that was just that it's the stimulation. It's how you energize the physical device you're testing, which also has been a really big insight for us, is that you really do want to hit the device with a set of signals that really elicits the behaviors of memory effects and on these nonlinear behaviors. And so it's that movement to signals that are realistic. And since most of these modern digital signals, going back to what Ian was talking about, are actually noise-like, right? They actually have high tone count, high data count, and they're approaching a noise distribution. This technique actually is quite important now.
It's you guys are bringing up excellent points here, and talking about the realistic signals going through here. I think that the next slide shows it. One of the this is something I didn't even think of as this method was first coming out, but it quickly became apparent this was a strong improvement in the method. So that noise power ratio signal that we've known and loved all these years, with the flat top and the notch, has always been intended to be a noise-like signal. with a very high crest factor, a very high peak to average power ratio, just Gaussian. It's effectively a Gaussian signal. But the fact is that might not be what we're sending through our satellite link. And so why would we measure the distortion created by a very high crest factor signal when we don't want to send, we're deliberately trying to avoid sending high crest factor signals through our satellite link. So one of the things that comes along with this method, since we're looking at the input and the output of the device under test at any time, and we can take that ratio at any time, you can use basically any signal to do this distortion test. You don't have to have an NPR test with a notch in it. So here's the slide really showed it to me. It's on the left side, I'm doing an NPR test with that classic NPR, noise-like high crest factor signal. And I've got my screen calipers up there, and I'm measuring the noise power ratio. On the right, I'm doing the same test, except I'm doing it with a single carrier signal. I think this is a 64 QAM signal that I'm using here. And the noise power ratio is 5 dB, different, 5 dB better with that signal. And I, in big letters at the bottom, I put fail and pass to throw fear into people, like, oh my gosh, we would fail this amplifier with an NPR test, but under the conditions of our signal, it might very well pass. At the end, we're really, designers are trying to squeeze every tenth of a dB out of these power amplifiers as they can, because power is everything. Power and power efficiency is everything. If I can get a little more power through, I can get a little more data through, or I can get a little more footprint. And so the question is, how hard can I push this amplifier? And you want to do that with a real-world signal. I don't show it here, but a lot of people that are working with OFDM signals in 5G and in space, and they are writing papers every month about how you can reduce the crest factor in these, because OFDMs are notoriously high crest factor. It's just horrible for a space environment. But so they've got all these different ways with symbol tricks they can do with symbols and coding and things to reduce that. Well, how do you know if it's working? This test shows you perfectly well how it's working. Take your signal that you just designed, use it to do this test, and measure your distortion. So
That's
yeah,
great.
I'm not. When I take it out to customers, they had no idea we could do anything like this, and it's like seeing stars in the daytime for them. That they can it really opens up what they can see.
Perfect. And this is all based on the PNAX, which is that better kit that's in everybody's lab. It's
yeah, you talk to customers about the advantage of this, and they say, oh, you can use your signal, and you don't have to use an NPR signal, and we can gauge the input and the output and so forth. But really, one advantage that presents itself on a more practical level is if you're testing a power amplifier, if you're testing an up converter or another component, you're probably already using a network analyzer for most of those tests already. And we put together a slide here that shows it's like, for an amplifier, you're already probably using this network analyzer to test the S parameters and the match and the compression and maybe things like power added efficiency and K factors and all those things. And so people were saying, okay, now especially for flight hardware. For flight hardware, every time a technician picks up a wrench, a manager lets out a little yelp in the back because it's just horrible. It's time, risk of damage, and it's just like every time that happens, there's a little cringe in the back of the room. And so you want to test this with one device and one connection. That's our goal, really, is to be able to hook up this one component and say, I'm doing all those tests for you, and now I'm going to do NPR and ACPR. One thing I didn't cover here in this talk is you can also do residual EVM with the same measurement, because once again, it's just a question of distortion of power over signal power. And I think there's tons of references on our website about how you can do that. But people are asking you to do a residual EVM measurement of this component. That's in there too.
Oh, thanks, Donald. Look, we could stay here all day, but we're getting to our bottom of our allotted time. Is it Mark, Ian? Have you got any other questions for Donald whilst we have him here?
I don't think so. Not for me.
Oh, Okay, no, but it's, I mean, as I say, I've been working with this for a little while now as well. And as you say, Donald, it is like seeing stars in the daytime for a lot of people, because it's one of these capabilities of bringing together that wideband source with the network analyzer and that whole notion of measuring the in and the out of the device under test. It just makes it so much. It becomes, the thing is, once you start looking at the math of the process as well, it becomes so clear, the extraction of the linear and nonlinear components from the in and out of the device under test, that it's just it's a fascinating technique. And I know you've got a lot of material coming out and going to be becoming available soon. So yeah, we'll make sure that other people will publicize that as much as possible.
Yeah, Richard, I was just going to add to that. I think you really hit on it. It's that exactness of measurement and the repeatability and all the things that you get from a network analyzer, this capability to ensure that throughout the whole design cycle, supply chain, you can kind of go on a traceable standard. You can deal with things that are sometimes hidden, that you make a measurement and the impedance changes as you change the power. All those things are kind of taken care of under the hood in a network analyzer, and especially in the VNAX. The VNAX.
VNAX, yeah. Okay, so if someone's watching this and wants to know more, what should they do? Ian, we got some resources for those.
Of course, naturally. And you know, I love to promote the brochure. So I'm going to say go to the resource list on here and click on that brochure, give it a download, look through it for whatever you're interested in. It covers some of the modulation distortion here. We also have an application note by Donald, better satellite link distortion testing using the spectral correlation method. There's a video on down there, measure NPR using real-world signals, and a few more application notes about modulation distortion application on PNAX. So there's a ton of information here that you can find. So
yeah, and I think that video is a video demonstration that you did, Donald. So yeah, that's well worth 3 minutes of anybody's time.
Yeah, if you want to see the measurement actually going through, it's a good demo for that.
Yeah, great. Well, thank you, Donald. As I say, we're getting up to 30 minutes, so thank you ever so much for your time today. Thank you, the rest of the team. If you want to know more about modulation distortion and network analyzers, or have any questions, general questions, please use the Q&A box or the question box on the registration page. We'll respond to all of your questions offline now, and we'll whilst things are moving ahead. We'd also really appreciate if you could fill in our survey, which is in the widget bar below, or it should pop up after these closing remarks. Thank you for coming. Thanks again to our guest, Donald van der Weyt, and hopefully see you all again soon. Thanks very much. Bye-bye.
Thanks, everybody. Great to be here. Thanks.
thank you.
Welcome to Field Measurement Solutions, Episode 3 of Space Talk, a series of short and hopefully useful webcasts that will give you some insight into the space industry, as well as test and measurement challenges faced therein. My name is Richard Soden. I'm the Space and Satellite Application Lead at Keysight and a confirmed Space Geek. My background's in optoelectronics, laser systems, and instrumentation. I've been working at Keysight for over 15 years, and I'm based in our Swiss offices. I've been working in big physics, power amplifier characterization, digital pre-distortion for telecom applications, and for the last 5 to 6 years, I've been working exclusively on space and satellite applications. In this series of webcasts, I'm joined by my fellow space geeks, Mark Lombardi and Ian Furness. Mark has over 25 years of experience in power, time, and frequency domain measurements in devices and flight hardware, supporting satellite and modem developers with hardware-in-the-loop communication system verification. And for the last 5 to 6 years, along with myself, has been focusing on developing Keysight's satellite and new space test solutions. Ian is relatively new to the Keysight team, and before working as an engineer at Keysight, Ian owned his own electrical contracting business. Ian's always been a space geek, and he's very excited about the new space industry. When he's not working, he's busy getting his kids excited about science and engineering. In each episode of this series, we'll be joined by an expert guest speaker to talk about a specific challenge or measurement requirement in the market. Mark, Ian, and I will be chatting with these experts and asking them questions on the challenges and talking about the solutions that we can bring to the market. We hope that in under 30 minutes, we can all learn something new, have a little bit of fun at the same time. And please, if you have any questions, please put those into our Q&A chat from the widget below. We'll not necessarily answer them live. We'll try and answer as many as possible with my colleagues, and we'll follow up on every single question as that comes up. So this week, we're joined by Teresa Kmetovic, with whom we'll be talking about field measurements or measurement out in the field. Teresa graduated from UC Davis with a BSEE, with an emphasis on electromagnetic theory. She's also got a BA in environmental studies from UC Santa Barbara. She's been working with Keysight for over 10 years and is based in our Santa Rosa offices in California. And she's been working as a marketing engineer and product manager, supporting the X series signal analyzers before joining the FieldFox team as an application engineer. Most importantly, she just joined the Space and Satellite Solutions team, so she's a new colleague for us. So welcome to Space Talk, and welcome to the team, Teresa. So Teresa, one of the things I keep asking everybody in all of these is going to be, with regards to the title, which is around field testing today, why is that important to space and satellite customers? And I think that's really comes down to the whole global aspect of space and satellite. You basically could be anywhere, right? Where you want to make your measurement could be anywhere in the world, and you can't just take your benchtop equipment out in the back of the car, right?
Yep, that's absolutely true. So typically, our customers are the big satellite manufacturers, and then these satellite ground stations are all around the world, and so it could be anywhere. And having the ability to make tests out in the field anywhere easily and with a portable instrument is really, really important. Okay, so, well, hi, everyone. Thanks, guys. Thanks for having me here today. I'm happy to be here. And so today I'm going to talk about field tests in particular. And when we're out in the field making field measurements at satellite ground stations, there's key elements that need to be tested. So this includes the antennas, the transmission lines, the transmitters, receivers, as well as the overall system tests that need to be completed. So for antennas, we measure things like return loss, antenna pattern. For the transmission lines, we're looking at things like faults in any transmission lines. There's high power amplifiers that need to be tested in the transmitters, low noise amplifiers in the receivers. And then for the overall system level tests, of course, there's noise figure measurements that we need on all of the individual components, as well as the overall system level carrier to noise measurements, as well as things like EVM and bit error rate. And more recently, go ahead.
No, I was just going to say, so all of these are sort of like health tests, right, on the system?
That's correct. Yeah. So typically, the satellite manufacturers, there's a standardized set of tests and procedures. So all of this needs to be checked and verified while at these ground stations in the field. Yeah. And now with the deployment of 5G, so there's trends. So there's more movement to more complex modulation schemes. So being able to test EVM is really important, being able to test wider bandwidths, and also moving to higher and higher frequencies.
Yeah. So all of these tests, do you have to be like cabled up to something, or are these? I mean, the antenna, yeah.
Yeah, so, well, we're moving more now toward, typically, yes, we are cabled up on these measurements to test, but we don't always have to do that. So we can make over-the-air measurements, half-loss measurements. We can also, we've recently started supporting a 5G and R over-the-air demodulation, as well as 4G LTE over-the-air demodulation. So we're able to make measurements and look at different base stations as well.
Great.
So next slide, please. Or are there other questions?
You know, there's a lot of these tests on here. Do they really perform all these tests out there? Forgive me for being the new guy in all this here, but it seems like a lot to be doing on a Earth station there.
Yeah, well, so typically when the Earth stations are initially being deployed, yeah, you do need to make the whole suite of measurements and verifications of these measurements. But then there's also just a lot of tests for just installation or just maintaining the Earth stations. And then you're not performing all of the suite of tests at all times. All right, so to make these tests on these satellite ground stations, there's usually 6 major pieces of RF and microwave test equipment that we use. And so that includes a cable antenna tester, a network analyzer, a spectrum analyzer, a DC and RF source, power meter, as well as current and voltage meters. So in the past, we've had our technicians and engineers going out to these ground stations carrying multiple heavy pieces of test equipment. And that can be really heavy. It can be cumbersome to set up the measurements. And now what we've done with FieldFox is that we've incorporated all of these pieces of test equipment into one handheld device. So we support over 25 different types of measurements, measurement RF and measurement test equipment in FieldFox. And so now doing all of these tests and maintenance on ground stations has become a lot more easier, and it's a portable handheld package.
I have a question.
Oh yeah.
Oh, I was just going to say, if the other option is to be lugging a bunch of equipment out to these Earth stations to be doing these tests, what is the performance difference between this handheld and a benchtop? I don't see how you get that kind of excellent performance there.
Yeah, well, so actually, FieldFox is a very, very high-performance handheld analyzer. Part of the way that we're achieving this performance is that we have our own high-frequency integrated circuits in the product. But you're absolutely right. Our bench instruments, like our PNAX, Vector Network Analyzer, or our UXA Signal Analyzer, we're going to have superior performance in those instruments because we have better dynamic range, better sweep speeds, faster FPGA, wider bandwidths, we'll achieve better EVMs. But when we have similar instrument settings, so keep in mind, FieldFox, we're operating between 16 and 30 watts only of power in this little 7-pound handheld instrument. So with similar instrument settings, our measurements correlate to our high-performance bench instruments.
Wow, that's awesome. Thank you.
Yeah.
So Ian, this is, I have to say, whenever we go to a satellite show and we get the FieldFox out on display, it's one of these instruments that just attracts a lot of attention because of all it can do. And one thing I should point out, because it's not clear actually, is when you're talking here, we're seeing 5 different instruments on the slide here, right? But those are all the same. And there's one instrument performing all of these functions, right?
It's one instrument, yeah. And the nice thing about FieldFox is that all of these different functions can be added as a software license key upgrade. So as you're moving through your test requirements, or if your test requirements evolve over time, the product is easily upgradable to add more functionality. So on the screen, you're just looking at 5 different measurements, but we're actually supporting over 25 different types of RF microwave test modes on FieldFox now.
Yeah,
So
Richard, I was even thinking.
Yeah.
Oh, sorry. Yeah, go ahead.
No, I was just saying, could you repeat the number again? How many different test modes?
Over 25 different and growing.
Oh, okay.
So
Okay,
this is a platform. Yeah, I think that the way I always like to explain to our customers is that if there's a piece of test equipment out there making a measurement for them, they're always asking, can we add that feature or functionality into our field Fox? People really like having the ability to just take one piece of equipment and make all of their measurements.
Yeah, and Richard, you were mentioning the trade shows, and it's really funny, even though this is very much intended to be a field, out in the field, easily usable hand carry tool. We've seen some small startup companies where one box fits all, right? They can actually get a lot done with a tool like this.
Yeah, I was going to say the same thing. I've seen, people, there's a huge return on investment on this, right? Because it's incremental. Instead of buying a new instrument or whatever, you just go you install the new firmware and get the new functionality and install the software. It's got all that inside to, as you say, Mark, respond to those sort of dual Swiss Army knife activities.
Or if you're in a global pandemic and you need to grab a piece of equipment to take home so you can still make measurements, I think it might be the one to grab.
Yeah, exactly.
Yeah. Yes. During the quarantine, I have mine here. It was very easy to take home and bring it with me, which was nice. Yeah. I think that segues nicely into the next slide. I did want to talk a little bit about how we're addressing the current technology trends in the market and what new options we've added to Field Fox. So we always continue to add new features, and the latest features that we've added support the 5G. So 5G is really big. It's a topic everywhere, and the 5G base stations will need to be tested. And we've added a new mode where we can measure the synchronization signals from multiple base stations in the vicinity. And we can provide metrics like the base station physical cell ID. We can provide the synchronization block index information, as well as key power metrics. We can look at frequency drift issues, as well as measure the base station EVM. So that's one of the new features that we've added. And then another feature that we've added, so the spectrum's becoming more and more crowded, and there's more and more interference. And one of our features that's of huge interest to satellite customers is our 100 megahertz of real-time bandwidth. So in the past, if you're in spectrum analyzer mode, the local oscillator is sweeping across frequency, but in real-time mode, the local oscillator is fixed, and our FPGA is processing over 120,000 FFTs per second. These FFTs are overlapped. So this is actual gap-free capture, and we're able to look at intermittent pulses. I think we're able to see things like weather radar pulses, things that you've never really been able to see before. And this is really, really great for troubleshooting, especially when you're out at a satellite ground station. Another feature that we've added, so phased array antennas. Phased array antennas are going to be deployed in 5G. They're also used in satellite. So we have a new phased array antenna solution, operates at 28 gigahertz Ka band. And so we're actually able to look at azimuth and elevation and actually see where the energy from the phased array beams are being focused in the environment. And finally, we're also addressing higher frequencies up to 110 gigahertz. We support connection to OML mixer head down converters covering different frequency bands. So we're able to meet the higher frequency requirements as well. You guys have any questions about that?
Well, I think the whole 5G satellite subject is huge. There's a lot of activity going on with 3GPP at the moment. I think that whole notion, the ability to look out for interferers, it's going to be really powerful for a lot of people, especially out in the field. That's like one of the things is identifying interferers. If you can see like little glitches coming up or leakage from one yeah, from one antenna into another, or there's so much stuff there that's useful. It's just
even regulatory wise, there's so much about, right, with LEO constellations, they have to actually be cognizant of when they're in direct line of sight of existing geo satellite and others. So it's really this interesting it's a much more dynamic environment than we've ever had. And a tool like this being able to be where you need it to be is pretty exciting.
Everyone is vying for bandwidth, and they're all quite crammed in one next to the other. So yeah, no, that's great. That's great.
Yeah.
Well,
So
I
this
had a
is
question.
yeah, go in.
I was just going to say, if this gets taken out into the field and you are doing all these measurements, phased array with wide bandwidths, real time, what's the kind of battery life that you're going to get out of this when you're running that? Because it seems like it might be draining it. And what was the weight on it again? Because would I be able to pack around a bunch of extra batteries too? I don't know.
Yeah, actually, so first I'll answer the weight. So the product is really light. It's 7 pounds. It's really portable, designed for easy carrying. All of the work around making it easy to use, big buttons, easy to view display day or night. We even have a night vision display. So the portability of the product is something that's really easy to carry around. The battery life, so we have superior battery technology. I mentioned that we have the 100 megahertz of real-time bandwidth, and this is chugging a super powerful FPGA. So we have a specification of a typical battery life of 4 hours in this operating mode. So if you move to a different operating mode where you're not using as much power with the FPGA, you'll get even longer battery life. The other nice thing about the FieldFox battery, you can hot swap the battery in the field. The batteries are not very heavy, so you could carry some extra batteries with you. No problem. Yeah.
I'm going to have to try and work out what 7 pounds is in kilos.
Oh yeah, it's about three.
I have picked one up.
Yeah, sorry for the people use kilograms. I think it's about 3.2 kilos, I believe.
Sounds about right. It feels that seems about right from my muscle memory.
Yeah. Yeah. So.
Teresa, we should have had you pick one up there and shown us it live.
Oh, I know. I thought, I should have. I would have to run downstairs to get it.
Yeah, it's all right.
So, yeah.
But this is real field equipment that you can take.
I don't have one.
Yeah.
Yeah. So, back to your previous question. If we're cabling up with these measurements. So, as we're moving into the millimeter wave measurements with our OML frequency extenders and making those measurements. So we're typically using a horn antenna or connecting to our phased array antenna to make these measurements. So, yeah.
Okay.
So the final slide, I just so we talked about all of the different measurement capabilities. So our final slide, I think it just really gives a nice example of how many different types of measurements we can do on FieldFox. So it's really, really easy. You just you power the instrument on, you switch into modes. We support measurements like noise figure, so portable noise figure measurements. We have an internal GPS receiver. We have, I mentioned the real-time spectrum analysis, now the over-the-air measurements. One thing, measurement that's unique to FieldFox that is of particular interest to satellite ground station customers is we support a measurement called extended range transmission analysis. And so this measurement is done when you're making measurements on really, really long cables where the dynamic range in the cable and antenna tester is not sufficient. So what we do is we take two FieldFoxes. One is the source at the front of the cable, and the other is the receiver. So we're actually getting our full dynamic range of our spectrum analyzer mode, which is greater than 100 dB. So we're able to make measurements on really long cables So that's another feature that we offer on FieldFox. We also support connection to USB power sensors, so we're able to make conversion gain or loss measurements of up converters or down converters.
Yeah, I was going to ask about. I was going to just quickly ask about, a lot of these LEOs in polar orbit, especially Earth observation, are up in the Arctic Circle. So, how's the outdoor operating range and ruggedness of a tool like this?
That's a great question. So, FieldFox has definitely been designed specifically with ruggedness in mind. So our specifications are from -10 to +55 degrees Celsius. So the product works in extremely cold temperatures, also all the way up. I mean, we have people out in really hot deserts working with FieldFox. It's rugged. We drop test it on all 6 sides. In fact, we had a customer who dropped the product 150 feet down the tower, and the product was still functioning just fine. We did allow to trade it in.
Was that an accident?
It was an accident, and we actually just for the customers, peace of mind, we did allow the customer to trade it in. We gave a new one, and then we have it on display in our corporate office just to show how rugged the product is. It's IP53 rated, so it's not designed to be submerged completely into a bucket of water, but it can withstand heavy water ingress. It's rated explosive environment, so it can withstand being in the desert and a lot of sand. So just a really durable product. Yeah.
Fantastic.
Yeah.
Okay, we're getting to the top. Well, we're getting to the end of our allotted time. Has anybody got any other questions to ask Teresa? We all good? I think that was fantastic. Yeah, Ian, you're in. You know all there is to know about collateral. Is there some things that people watching this can grab and download for later perusal?
Yeah, I'd say my favorite place to start would be the brochure, right? So kick it off with the brochure. There's a video that's on its way about the B-series FieldFox as well. And then we have an application note, satellite Earth station validation, maintenance, and repair that would be really good to give a lot of examples of how this FieldFox is used out in the field. So fantastic. Those would be great places to check.
Okay, great.
And
I think those are
right here.
Yeah. Okay. Yeah, there's a widget somewhere around here.
Yeah. I think it's called a resource list. So check out the resource list in here.
Fantastic. Thanks, Ian. Okay. Well, thank you all. Thank you, Teresa. That was great.
Thank you.
And welcome again to the team. So if you have any other questions about field measurement or instruments mentioned here, the FieldFoxes, or if you've just got a general question, please put it into the Q&A or we have a question box on the registration page. We'll respond to all of your questions. We'll have tried already in the Q&A, and other ones we'll respond to offline. We'd also really appreciate if you could fill in our survey. There's a survey that's going to pop up in a minute once we're finished after these closing remarks. But thank you very much for coming. Thanks again to Teresa. Thanks to the team. And hopefully see you all again soon. Thanks very much. Bye-bye.
Bye.
Bye.
Bye.